All right, guys, so welcome to calculus. You guys would have had a lesson this morning just on recalling radicals and eliminating radicals from either the numerator or denominator, okay? And that's going to come into play this afternoon's lesson because we're going to see some questions where we're going to have to, like, rationalize a numerator or denominator, okay? And we're going to see square roots, okay? So the main thing that we're going to look at today, and typically with calculus, I suppose, is the difference between secant lines and tangent lines, okay? And for the most part with calculus, we're going to see predominantly tangent lines, okay, because they tell us something of instantaneously, okay? Whereas a secant line is more of like an average, we're going to come to learn, okay? So this entire lesson this afternoon kind of spins off of the fact that we have secant lines and tangent lines, and ultimately a tangent line tells us what the slope is at a particular point, okay? The relationship between the two is that a tangent line is essentially a secant line, with the exception that the average, which we'll see in the picture does a good job at depicting this, is very, very small, okay? So the difference in the two numbers in the denominator is very, very small, and we're going to see that here. That's just words to you. I'll show you in the picture what that actually means, okay? So the tangent line touches the curve at one point and is in a straight line that most resembles the graph near that point, okay? Its slope tells us how steep the graph is at that point of tangency, okay? Whereas the secant line passes through more than one point on the curve, right? And so we know if a secant line is just like a typical line that you would have seen in grade 9, where we had we'd have point 1, where there's an x1 and a y1, right? And then we'd have a point up here, point 2, where we had an x2 and a y2, right? And we could find the slope of that secant line, or the line, as you guys would have seen in the past. So this is a secant. We could have found the slope of that by finding the difference in change in the y's over the change in the x's, right? Which would be equal to y2 minus y1 over x2 minus x1, right? So rise over run, right? So secant lines measure the average rate of change, right, between 2 points, right? And so for today's lesson, we want to find the instantaneous, I'm going to try and spell this correctly, instantaneous rate of change, okay? And so we're looking at one specific point, right? And I suppose now at this point in time, we can take a look at the difference between these two graphs. So what I'll say is, not the graphs, but the two lines. The tangent will be in blue, right? And that's measuring the slope at this particular point right there. Okay, it's a representation of the slope there. And in red is the secant line. Okay. It's representing the average rate of change from this point to this point. Okay. Now, what I meant earlier by the denominator gets infinitely small, or approaches 0, I suppose. We're looking at h, we're calling the difference between these x values. Okay, so h represents delta x, or the change in how big is this? Okay, and so when I say the denominator gets really, really small, we're approaching 0. Okay, and we can use this to our advantage, right? Basically, it means instead of having a very large change in x value, we're interested in an h value that goes towards 0, which means the difference between these 2 points is very, very small, right? So we'd have like an h1, or sorry, not an h1, we'd have an x1 and an x2 that were very, very close to each other, right? Right at that point. Okay, so essentially we can say as h approaches 0, the difference between the x values, right? And I'm going to write an equation down too in this blank space here in a sec. The difference between the x values goes to 0. Okay, and so we can use this to our advantage, right, when trying to find the equation of tangents, right? So this is not that interesting. This represents the average rate of change between 2 points, right? You guys have been doing that since grade 9. What we're going to try and do here is switch it up in the sense that I'm interested in just one particular point in time, okay? And so that's what we're going to spend, that's calculus, right? So as we go through the first few units here, we're going to start at where some of the later material comes from, right? Almost like a proof, but it's not a proof. You can actually use it to actually do the exact same thing, okay? So that's what we're going to do today is find the slope of tangents, right? Either be it an equation or the actual numerical value of the slope, okay? And so we're able to do that by using this equation that looks pretty ugly, but after you do a few of them, it makes sense, and we're introducing this notion of as h approaches 0. Okay, and so we're going to say that the limit as h approaches 0, we're going to say this is equal to the slope, right? Slope is equal to the limit as h approaches 0 of f of x plus h minus the original function f of x, all divided by h. And remember, h is the thing that goes towards 0. So the problem we run into when we use this, and it kind of forms the foundation of things that you can do to manipulate what's gone on, is, well, if we have a 0 in the denominator, you guys would learn that that's not allowed, right? And so we're going to have to do something to the numerator in such a way that we can eliminate this h from the denominator. Okay? So that forms the what goes on here. Okay? So let's have a look down here, okay? So using this, slopes can be found for tangent lines along the curve at various points, okay? If you were to come up with the generalized equation, then you could plug in a whole bunch of x values and get the slopes out at those each individual x values, which is exactly what we're going to do down here, okay? So we want to find the slopes of the tangent lines to this equation, but at each of these x values independently. Right? And so we should expect to see different values of, or different slope values, right? If it's a curve or a different kind of graph, right? This is not a line, so we know we're not going to have one uniform slope, okay? It's a parabola of some sort, right? A quadratic. And so I expect to see a whole bunch of different tangent lines that might be at different slopes. Really steep, really shallow, negative, positive, right? Should expect to see a whole bunch of them. And so here's what we need to do. And this very, very much comes, as I was figuring this out, this very much comes down to organization and being very, very careful. And I don't think you can write too many lines, if that makes sense, right? So you'd be very thorough in what it is you're doing, okay? So what we want to find, well, I'll write out the function, right? We're going to have y equals 2x squared plus x. Okay, and so I want to take the equation and I want to replace it with, let's ignore these until the very end, okay? I want to figure out what the equation of the tangent line is. That's what I'm after, okay? And so I'm going to use this right here. Okay, so I'm just going to write out the fact m equals the limit as h approaches 0, right? Very small differences in the x values of f of x plus h minus f of x all divided by h. Okay? Now, this is just a generalized thing. We haven't done anything yet. But what I want to see, and this is just, personal preference, it seems to have worked for me in figuring all of this out. I want to write the equation f of x plus h. I want to write that out. Okay, so what this means is, if you guys recall, it doesn't matter if f of negative 2, you guys learned that whatever's in here, you replace as the x value. It could be a function, could be whatever, right? So this is all we're going to do. We're going to replace everywhere I see an x in the original equation, I'm going to replace it with an x plus h. Okay, and so you're going to get something else. You're going to get 2x plus h squared plus x plus h. And then obviously, this is just the function f of x, right? Maybe I should have wrote it like that. F of x is just the original equation, right? So f of x is equal to 2x squared plus x. Okay, and it's these two things. You can now take this and you can plug it into here, right? This whole thing is equal to f of x plus h. And you could take the original function and plug it back into there. Okay, and don't forget to divide by h, because I did that this morning too, and that gave me some problems. Okay, so here's what we're going to do. You're just going to replace everything that's in there with the two things that we just found, or wrote down. I haven't really found anything yet. So we're looking at the limit as the 2x values approach 0, or h, right, of 2x squared, x plus h squared plus x plus h, and then don't forget to subtract off the original function, 2x squared plus x. All of that needs to be divided by h. Now, this is what I was alluding to earlier, where we're trying to work out a way, by being clever, to get the h to cancel out of the denominator, because if I go to evaluate this at the very end, right, all I'm going to do is say, okay, well, I'm going to actually check to see what the limit is by plugging in what the h value is, right? And so if I'm still in the position where if I were to actually plug in the h value of 0, I still have a 0 in the denominator, okay? So we need to do a little bit of work to try to get that h to cancel in the denominator, okay? So how do we do that? Well, let's just expand and collect like terms in the numerator, okay? So the limit of h approaches 0. What are we going to get for this? Well, we're going to get 2 times x squared plus 2xh plus h squared. You recall this would be the result of going x plus h times x plus h if you distributed. Okay, that's what you would get. And so that takes care of this. And then we're going to do, okay, well, we have a plus x plus h minus 2x squared plus x, all divided by h, okay? I would distribute the 2 in and see what happens, okay? And then we can collect like terms. So let's do that. We get 2x squared plus 4xh plus 2h squared plus x plus h minus 2x squared plus x, all divided by h. Okay. Now, sorry. And this is me, I'm thinking out loud here, and I'm catching things as I move along here. It's minus whatever the function, and this is important. This is what I'm saying, like, it's important, and I make mistakes like this all the time, and then I catch it, right? But it is possible sometimes you do the work and then you don't catch it. So I'm going to do one other thing here. It's minus this entire function, which changes things. The presence of the brackets changes things, because now, to write this line out here, you have to distribute the negative into both things. right, from the original function. And so I'm going to have a minus 2x squared minus x, okay, by just pure, that's what it's telling me to do, okay? So just be careful with that, and this is what I'm saying. The more steps you guys show, the easier it is to find a particular error. And I got carried away yesterday trying to do too much at once, and I make little sign errors, and then I get the wrong answer, okay? So I don't think there's a, for the first time doing this stuff, it's okay that these questions take up a lot of room, right? Because you're being very thorough, and just be careful with what goes on here, right? So you'll notice now, this 2x squared minus a 2x squared, those are going to cancel, right? 2x squared minus 2x squared is 0. And then you can see, okay, well, x, take away x, that's going to cancel. And it doesn't look like there's anything else in the numerator that could create a 0 pair or cancel with one another, right? And so you're just going to rewrite the numerator. As h approaches 0, you're going to see that, okay, well, I get 2h squared plus 4xh plus an h, right? I see the plus h there. So those are the three things that are left over, right? And all of that has to be divided by an h. Now, it's at this stage, I'm almost out of room here, but we're almost done. If I still plugged in the h value, you'd still have the h in the denominator, right? So we got one more thing to do, right? We could say, okay, well, let's factor out. It looks like I have an h in all three terms up in the numerator now. So that means I could remove a common factor of h. And that divides by h. Well, look at that. Now if I've removed the factor of h in the numerator, these cancel. And I have the ability to do this, guys, so I'm just going to do it. I'm going to shrink all this stuff down, give myself some room, if it lets me. Okay, and you're left with the thing in the numerator. Well, how do you do this? Well, you just check it now. You can take the h value and plug it in, and what do you get? Well, m equals, I guess this would be almost the equation of the tangent. You'd get 2 times 0, that's going to cancel. You're going to get 4x plus 1. Okay, that represents, as we'll come to learn, m will be what we call, we're going to learn this stuff as we go through here, m, the slope, will turn into what we call f prime of x, right? That's what we call the differential, okay, or the derivative. Okay, so the f prime of x is equal to 4x plus 1. That's the equation of the tangent, right? The line that represents the slope at any point along that curve. Okay, now what we're going to do, the second part of this question, remember, asked us to actually calculate what the slope value was at each of these 4 x values. Okay, so we're just going to check those. You have the equation, that's the important part. Now you can check what the slope is at each one of those x values. Okay, so that's what we're going to do. We're going to say, okay, f prime of 3 has to equal 4 times 3 plus 1. Well, that equals 13. And if I check f prime at 4, that's going to equal 4 times 4 plus 1. That's going to equal 17. Okay, and f prime at 7, that should equal 4 times 7, right? Plus 1, which is 4 and 4 is 16, plus another 12, 16, 26, 28, plus 1. Okay, and then f prime at 100, 4 times 100 plus 1, be 401. Okay, so what do these represent? This is the slope at each of these values. Okay, so that's your first taste of this equation can be a little bit tricky. Okay, it always follows this form. What I've found over the last couple days in doing some of these questions to prepare for this, I've found that this has been the number one thing to get me through these questions. Okay, and if the question provides you with a specific x value, then replace it in the actual in the pieces. Okay, hopefully we'll see one of those questions. I think I did that somewhere on here. Okay, so let's go down now and fill out the rest of the. Okay, so the difference of the values of f of x is known as the differential. Okay, this is the main operation in differential calculus. It is also what we call, and this is what I said before, what we call the derivative, which we labeled as being f prime of x. Right? The differential or derivative, which finds the slope of the tangent, is identified using any of the following notations. Okay, so here's what we've got. We've got f, we've already done one, f prime of x, right, which reads f prime, I'll write these all down. Okay, and I suppose you could change the word of out to at f prime at x, right? The slope at x is probably a better way of saying it. You could have this one, dy dx, which reads okay. Okay, those are the two ones that you're going to see. This just simply means we're going to derive equation y with respect to x. That's what this means. Okay.